Hello, my name is Kučerová and I am a master student at the Czech Technical University in Prague. In this video, I would like to present our work called Variable Speed Traveling Salesman Problem for vehicles with curvature-constrained trajectories. Our motivation is to determine a tour over multiple locations that minimizes the travel time of the vehicle moving along a curvature-constrained trajectory. Finding the sequence of visits to the locations is a problem known as the Traveling Salesman Problem, or TSP for short. The TSP is known to be NP-hard. In our problem, we also need to satisfy the vehicle's motion constraints expressed by curvature-constrained trajectories connecting the locations to be visited. Therefore, we base our proposed solution on a solver that accounts for the additional complexity. To decrease the travel time, we take advantage of our previous work, a trajectory called the multi-radius Dubins path that exploits a variable turning radius. The trajectory is inspired by the Dubins path, which is computationally effective. So, what is the multi-radius Dubins path? First, let me briefly introduce the Dubins path, which is the shortest curvature-constrained point-to-point path for the Dubins vehicle. The Dubins vehicle is a model of vehicles with a constant forward speed that limits its minimum turning radius. In this work, the Dubins vehicle is considered with multiple forward speeds and limited acceleration. A variant of the TSP exists for the Dubins vehicle and it is called the Dubins TSP. In general, the Dubins path consists of three segments, which can be a straight line or part of a circle with a fixed radius. The path is calculated between two configurations with a closed-form expression, and it is computationally efficient. The multi-radius Dubins path is inspired by the original Dubins path. It also has three segments, where the connecting segment is always a straight line because the circle part in the middle is used rarely and only for very closed endpoints. However, the radius of the circle part can differ for each configuration. By using a different turning radius on each circle segment, the travel time of the trajectory can be reduced. This is because the speed can be increased on a larger radius, but it also makes the trajectory longer. Therefore, the trade-off between increasing the speed and prolonging the trajectory must be found to decrease the travel time. The closed-form expression exists for the multi-radius Dubins path if the turning radii are specified, and computing a single trajectory is computationally efficient. Because the used vehicle model has acceleration constraints, the speed must be continuous throughout the whole trajectory. It also has to be continuous throughout the whole tour over multiple locations. The maximum speed of the vehicle on the trajectory is limited by the radius. It is defined that the maximum speed for a given radius must be used at trajectory endpoints. Therefore, the connectivity can be ensured by specifying the radius with the configuration at each location, because the same radius at each endpoint implies the same connection speed. Let's see an example of the tour over multiple locations when the multi-radius Dubins path is used. The animation shows an example solution of the tour over multiple locations found by the proposed solver. Different turning radii can be seen in the trajectory. The used vehicle motion constraints are inspired by the Cessna aircraft. The vehicle speed at the tour is encoded with color, where the blue color shows the slowest speed and the yellow color the highest speed. The example shows how the vehicle can situationally change its speed based on the mutual distance between locations. A variant of the TSP with curvature-constrained trajectory and variable speed formulated in this paper is called the Variable Speed Traveling Salesman Problem, or the VS-TSP for short. The multi-radius Dubins path is used for calculating trajectories between two configurations. For the TSP, however, the trajectories must be connected together over multiple locations. When only locations are assigned, the vehicle heading angle at each location has to be specified to allow the point-to-point trajectory computation. This is already addressed in the Dubins TSP. In the VS-TSP, it is further required that the vehicle speed is the same for arriving and leaving trajectory to and from the location because the acceleration of the vehicle is limited as well. Both heading angles and speeds are discretized in a given range, and the samples are used to create the configuration for the multi-radius Dubins path. Some trajectories for a particular combination of increased speeds might become infeasible, but we always include the minimum speed for the minimum turning radius, therefore the solution can always be found. To solve the VS-TSP problem, for each location we discretize the vehicle angles and speeds that represent possible turning radii. Every two locations then have k squared L squared possible connections, where k is the number of possible heading angles and L is the number of speed samples. In the animation, you can see the changing heading angles of the middle location with multiple trajectories representing the different connection speeds. The sample structure over all the locations is represented by the graph structure from which the tour is obtained. When the sequence of locations is specified, we need to select the heading angles and speeds so we can plan the tour, which defines the graph structure shown in the figure. Each location has samples of both parameters that are paired into sample combinations. One sample combination at each location is selected to create the tour. It turns the location into a configuration, and then the multi-radius Dubins path is computed by the closed-form expression. In fact, the multi-radius Dubins path between all sample combinations can be pre-computed, and its travel time can be saved to avoid repeated computations during the travel time optimization. Selecting the fastest tour from the sample points has the time complexity of the order n times k cubed times L cubed. The objective of the VS-TSP is to minimize the travel time over the whole tour, which also includes finding the best sequence of locations. For finding a solution to the whole problem, the following solver is used. The solver simultaneously searches for the tour in two optimization parts. First, finding the optimal sequence of locations, and second, finding the trajectory feasible for the vehicle model with varying speed. The initial solution is found by the cheapest insertion. 3 locations are randomly selected at first that form a sequence, and the rest of the locations are iteratively inserted into the sequence using the cheapest insertion strategy. The solver examines all sample combinations when inserting the location to ensure that the vehicle constraints are fulfilled. The initial solution is then improved upon with the variable neighborhood search, or VNS for short. The VNS is a combinatorial meta-heuristic. It randomly modifies the found sequence by the shake operation at first and then enters the local improvement phase. If an improvement is made, it selects this solution as the new best and iterates the same approach until the stopping condition is met. The addressed VS-TSP is an extension of the NP-hard Dubins TSP, and therefore the computational complexity is high. The number of possible values of the variables in the solver is large, and a higher number of combinations result in more sequences to be evaluated than in the Dubins TSP. We want to compensate for that, and to do it we use the fast sequence rejection, which is based on a computationally efficient estimate of the tour cost. In our case, finding a lower bound estimate is quicker than finding the best samples for the whole tour, and by using the lower bound values we can quickly reject the solutions that would likely be worse than the current best. Next, let's examine the proposed approach in different scenarios testing various properties. The VS-TSP considers multiple parameters in the travel time optimization. The results are obtained on instances with various properties. These are the number of locations n, but also the locations density rho, which is specified as the number of locations in a square area relative to the minimum turning radius. The minimum turning radius of the vehicle must be specified, as well as the speed and acceleration limits. In the following results, constraints of the Cessna aircraft are used. The quality of the solution is influenced by the number of heading angle samples k, the number of speed samples L, and the maximum computational time, which has been used as the stopping condition of the solver. The sampled parameters can be seen in the bottom right image. Now, let's look at the influence of the instance density. We examine the cost for different densities to see if the proposed method is beneficial in all cases. The plot on the left shows the cost for different speed sampling. The minimum speed is more beneficial than the maximum at more dense instances, and vice versa for the smaller density. Using multiple speed samples reduces the cost for all considered densities. The density of the instances determines the resulting use of turning radii when multiple connecting speeds are used. On the right, you can see the tours found for different densities with 5 speed samples. It can be seen that for the highest density, the minimum turning radius is used the most, as high maneuverability is preferable. For low densities, on the other hand, the vehicle uses the maximum speed for the majority of the tour, as the locations are mutually distant. The results support that using different radii can be beneficial, even if we do not know the instance beforehand. Now, let's look at the solution quality for different computational times. The scenario displays the solution travel time improvement during the computation. Because we use the variable neighborhood search, the results can improve over time. This test shows how the improvements happen after longer computation. This test is done with a different number of speed samples, specifically minimum and maximum vehicle speed, and then 3, 5, and 10 speed samples selected exponentially in the range between minimum and maximum speed. The earliest solution is found when using only one speed. The more speed samples are used, the longer it takes to find the initial solution. The initial solution, when using a larger number of speed samples, is however better in comparison to using only one speed. The initial solution is not improved linearly with the number of samples, as it can be seen on the improvement between 3 to 5 versus 5 to 10 speed samples. The results, however, improve for an increasing number of samples despite adding the computational complexity. This is important as the larger number of samples results in a solution that is closer to the optimum. Next, we examine the influence of the other sampled parameter. Let's take a look at using a larger number of heading angle samples with 5 connecting speed samples. All instances are run with the same computational time, and the improvement is reported after a few time milestones. The results show that a larger number of angle samples leads to an improved solution cost, the same as in the previous test. However, as the required computational time increases with the number of samples, the solution was not even found within 100 seconds of computation for 20 heading samples. The two tests show that the benefits of using a larger number of samples must be taken into account with the downside of longer computational time. Finally, we look at the effect of the fast sequence rejection. The influence of fast sequence rejection has been examined to show how the technique helps to decrease the computational time. The technique provides a rough cost estimate at first, which is fast to compute. If the solution passes a certain bound, a more precise estimate is computed, which also takes a longer computational time. Otherwise, the solution is rejected, thus the name fast sequence rejection. Most improvements are found for the initial solution, hence the higher computational time. Later over the computational time, the average time of comparison is decreasing as the evaluated sequences are rejected earlier. The converged line that is horizontal towards the end of computation corresponds to the time of rough time estimate computation, where the majority of solutions are rejected. To conclude our work, we proposed the variable speed traveling salesman problem formulation, which aims to minimize the travel time instead of tour length while considering the motion constraints of the vehicle. The proposed solution takes advantage of the existing Dubins TSP solver and extends the discrete samples with the speed samples instead of only the heading angles. This modification allows the employment of the multi-radius Dubins path. The travel time of the found tour decreases up to about 20% when using the multi-radius Dubins path that exploits different turning radius at each circle segment. Because the number of samples is increased at each location, the computational complexity is increased. In the proposed solution, it is compensated by employing the fast sequence rejection technique. For future work, it would be interesting to find a lower bound of the solution for the VS-TSP. Also, the time of finding the initial solution could be decreased with lazy pre-computation. Another possible extension is to use the method for 3D trajectory planning. If you have further questions, don't hesitate to contact us. Thank you for watching.